Hello, everybody. My name is Kilian Vos. Today I'll be presenting on CoastSat, which is an open source toolbox for mapping shorelines on publicly available satellite images. So first of all, thank you very much to the organizers from IGCP, especially Christopher Klein, for inviting me to this workshop. It's a real pleasure to be presenting here. And I also like to thank my co-authors, Christian Splinter, Mitchell Harley, and Ian Turner, who were my PhD supervisors when I did this work at the UNSW Water Research Laboratory in Sydney, Australia. So let's get started. Here, I'll first present satellite remote sensing and why it's become so popular for coastal monitoring in the last 5 years or so. And then I'll introduce the CoastSat toolbox, which you can see a snapshot here, and which algorithm we're using to map that sun-water interface. And finally, at the end, I'll provide some example applications of real-world problems where this data can be used by coastal scientists, managers, and also engineers. So let's get started. Firstly, coastal erosion. It's a huge problem around the world. So there's a lot of infrastructure and natural habitat that is at risk of coastal erosion. And so it's very important that we understand it, that we are able to model, forecast, and predict those changes. And that's the topic of this workshop. So here I'm showing a pre- and post-storm UAV survey of Narrabeen in Sydney in 2016, and you can see how this coastal storm just ate 50 meters of beach width overnight and destroyed all the beach-facing infrastructure. So that's a change that happens very rapidly, but coastal change can also happen at the longer timescales. So here's an example of beach rotation, the beach south of Sydney, where you can see a satellite image where all the sand was at the southern end of the beach, about 100 meters of beach width here. And 3 years later, in 2016, it's all gone and it has moved to the northern end of the beach. So this is known as beach rotation, and it happens much more slow. It happens slowly, so over 3 to 5 years, and just oscillates. So to understand this complex coastal processes, we need monitoring, and that's where I'd like to focus on in this presentation. So here's Professor Andy Short. He lived in Sydney, and in the 1980s he started surveying the beach. He's one of the pioneers in coastal monitoring, and he would go out with his pole and monitor, survey 5 profiles at Narrabeen in Sydney. And the part of the beach that Andy was measuring is the subaerial beach, so basically from the dune to the waterline. And the proxy that we will be using in this presentation for coastal change is actually the beach width. So it's not a volume consideration, but it's just the width of the subaerial beach that we're looking at. And that's what we can see with the bird eye view with the satellite. So here's a 40-year data set from Andy Short. It's publicly available at this link. So he started in 1976. And here's the beach width where I subtracted the mean over time. And you can see how valuable this data is. Now it's a treasure of data. You can see the interannual cycles, seasonal cycles. You can see big events like that 2016 storm. So this data set can inform coastal management and has informed coastal management at this site because it provides coastal change at different timescales, storm demand, habitat, and amenity. There's a lot of indicators that we can derive from having this data available. However, there's only a handful of sites in the world that have such rich coastal monitoring programs, or maybe 10 sites. And most of the world's beaches are actually not covered by any in situ data. So what do we do with the remaining 99.99999% of beaches that don't have in situ coverage? So one option that I'm talking about here is using Earth observing satellites. So these satellites have been orbiting the Earth since the early 80s, and they take an image of the same point on Earth every 2 weeks, including the coastline. However, the challenge with this imagery is that it's quite coarse, so it's medium resolution satellite imagery at 30 meters per pixel, and more recently it's gone down to 10. So I'll show this little app where you can see all the objects that are currently orbiting the Earth. So it's absolutely crazy how many there are. There are thousands of satellites around the Earth, all with different purposes. And the ones that we're looking at here are Earth observing satellites. So they're relatively close to the Earth. I'll take an example. So Landsat 8, for example. So it's now between Antarctica and Australia, and it's 700 kilometers from the Earth. And it's revisiting the same point on Earth every 16 days and taking an image at 30 meters per pixel, a multispectral image. So it provides repeated measurements of any point on Earth. So if we summarize a bit the information from all these satellites, so we can break it down into optical imaging satellites, so they're passive sensors that take images, and then we can divide them into commercial and publicly available. Here I'll be showing only publicly available derived product. So from the Landsat program, we can start in 1984 with Landsat 5, which is at 30 meter resolution, 16 days revisit. And then we can include Landsat 7 and then Landsat 8 and Sentinel-2, which are more recent. And Sentinel-2 has 10 meter resolution, 5 days revisit, which is quite outstanding. So these are the satellite missions that are used in CoastSat. They provide global coverage. You can access them via Google Earth Engine, so there's no need to download the imagery. CoastSat can directly retrieve the imagery that you need via Google Earth Engine, which has a full copy of the archive for those satellites. And the toolbox allows users to map 35-year, or some areas almost 40-year time series of shoreline change from the satellite imagery. We did the thorough validation on these satellite-derived shorelines, and the accuracy is about 10 meters horizontally. And the code is open source on GitHub, so you can use it. You can post any issues that you have there, and there's a community that responds, community of users. So now if I go back to Andy Short's dataset, and we overlay the satellite-derived shorelines on top at the same profile, we can see that we actually get a very good match. So root mean square there is below 10 meters, and we are able to pick some of the interannual signals. So we're able to provide valuable data just with the satellite this site. So how does the algorithm work? So I'll just give a quick technical description. So if this is a Sentinel-2 image of Narbin at 10 meters per pixel, the first thing that we do is we download the image for the region of interest with all the multispectral bands that are needed. And then the image is classified. So each pixel is labeled as sand, water, which is a deep water, and white water, which is like the aerated water. So when the wave breaks on the shoreline, for example. And all the other pixels go in another class, the roads, the buildings, the forest, etc., because we're not interested in those. Then we calculate the water index, which is an index that uses the shortwave infrared and provides a lot of contrast between water and land pixels. And then we look at the distribution of this water index for 3 classes. So here you can see in blue the water pixels, in orange the sand pixels. And the other classes have very wide distribution, so we remove them. And then we calculate a threshold automatically, which is called Otsu's method, which is the threshold that best divides two distributions. So here, the Otsu threshold differentiates the sand pixels from the water pixels is about -0.1 MNDWI, water index. So then we take that -0.1 threshold, we go back to the MNDWI image, and we can contour that threshold at sub-pixel resolution. So here's the contour. So that's the -0.1 threshold map on the image. And that's our water line for this image. And we can run this in a loop over all the images that are available at this site. And you can see it's quite robust at mapping the water line. So it's consistently getting that sand-water interface with the Otsu threshold between sand and water pixels. So that's the basics behind the algorithm. Now the processing, so once you have all the shorelines, they're 2D, so we need to convert them to time series. So this is also done in the toolbox. So you can create some cross-shore transects along your beach and then extract a time series of a cross-shore change along that transect. Here, for example, we can see the impact of that 2016 storm, where about 60 meters of shoreline were lost, were eroded. There's a very important aspect of this is that we need to apply tidal correction. So every image is taken at a different stage of the tide. So we're mapping the water line. So to convert that water line into a shoreline, we need to remove the tidal effect. So we know the time which each image was acquired. And if we can link the imagery to a tidal model or a tidal data set of that site, we can then correct for the tide. So we remove the tidal effects from the time series with this very simple formula. And you also need to know the beach slope. So if you don't have the beach slope at your site, there's also a toolbox, CoastSat-slope, which helps you to estimate that beach slope using satellite-derived shorelines and a global tide model. But you can see it's very important to apply tidal correction because some images are taken on a king tide here, and then some images may be taken on a low tide. So there'll be a big change just due to the tide. Water level correction is a very challenging problem. So I invite you to read, I think this latest paper on Constantine et al. 2023 is very interesting on which water level correction can be applied to satellite-derived shorelines. It's also the limitation of these satellite-derived shoreline products is that we're mapping the water line, not the shoreline. So there's a bit of a difference there. So on a high tide imagery, the water line is a very good proxy. You can see here at a macro tidal site in France. But then if we take another image at the low tide here, the water line doesn't make any sense, because the intertidal zone is very complex. There's shoals and bars. And so what can you do with that water line at low tide? So there's different ways of doing it. You can discard all the low tide images, but this is the main limitation of this kind of tools, is that meso to macro tidal sites are very difficult. A bit more on this, we did a benchmark of all different algorithms, 5 different algorithms actually, across 4 sites that had long-term monitoring programs. 2 microtidal ones, 1 mesotidal, and that macrotidal one in France, Truc Vert. And you can see how the accuracy, that's R square, for the 5 algorithm just decreases as the tidal range increases. And the root mean squared error that we're getting were around 10 meters for macrotidal beaches, but then all of the algorithm had errors more than 20 meters at the Truc Vert, so high energy macrotidal beach. So it's a consistent issue across all the algorithms, and it's something that people are actively working on to find a solution so that we can extend satellite-derived shorelines to these macrotidal environments. So now I'll show some nice applications of these satellite-derived shorelines. So, for example, here's a beach nourishment in Florida, St. Pete. This is the location of the Coast Sediment Conference in 2019. So that was just in front of it, and there's this big nourishment that occurred. So we can use the tool there, map the shorelines, then put a transect through that section, and then look at the time series. And you can see here's a 35-year time series, and you can see all the nourishments, how the magnitude of the nourishment, the frequency, how long they lasted. And this can be very useful for coastal managers to do a coast benefit analysis, to see where's the best place to do the nourishment, how much, etc. So that's really useful information, and it's a signal that is very strong. So about 200, even 300 meters of shoreline accrete in one short amount of time. So that's can be captured by a satellite with a 10-meter accuracy. Another application that I think is really interesting is from a colleague at University of Western Australia, Mike Cutler. He developed this tool to map the contour of coral atolls and the area of sand, and also the shape of the island and how it responds to the wave climate. So that toolbox is also available, CoastSat.islands. I think it's a very interesting application, as those islands are very dynamic as they respond to the wave climate. Another example that I worked on is looking at the impact of ENSO on shoreline change. So we derive satellite shorelines every 100 meter, more than 8,000 kilometers of coast, mostly macrotidal coast in the Pacific Rim. And then we look at the anomalies during El Nino and La Nina periods. And we could see during El Nino winters, we have significant enhanced erosion along most of the eastern side of the basin, so from California to Chile. While during La Nina phase, that erosion occurs in Southeast Australia. So that was something that was already observed in situ, but we could really capture it coherently at a large scale using satellite data. There's, I think, several thousand beaches in this data set. And it's also available on this website if you want to look at the data. So that's another application showing how the satellites can be used to upscale some analysis to look at climate effects and how the coast responds to these climate patterns. So yeah, I'll conclude. The main take-home message from this presentation is that satellite-derived shorelines are now capable of tracking the position of the shoreline with an accuracy of about 10 meters in macrotidal environments. So that's very useful for a lot of applications. It's sufficient. Looking at long-term trends, looking at beach nourishments. You just need to have a signal that is, let's say, at least 20 meters, so 2 times the accuracy, to have a good enough signal-to-noise ratio. However, along meso to macrotidal beaches, that accuracy is much lower, so 15 to 20 meters for those in those environments. But often, satellite-derived shorelines is the only source of past shoreline information, in addition to aerial surveys, photogrammetry, which is usually more sparse, maybe once every few years. And it's low-cost shoreline data, because there's a lot of tools that are publicly available. The imagery is publicly available. So there's not a lot of cost, is mostly running the scripts and a lot of time processing the data. And the time series that you can extract have around monthly temporal frequency. It depends on the cloud coverage of your region. In Australia, we're quite lucky with low cloud frequency, so we get a lot of images that are cloud-free for mapping the shoreline. And with that monthly frequency, you can actually capture changes that go from long-term trends to interannual, and even seasonal shoreline changes can be observed with monthly frequency. The main challenge, as I said, is accounting for water level fluctuations, and especially along meso to macrotidal coast. And finally, there are different algorithms that exist. So CoastSat is one of them, but I invite you to also look at SIAET from Valencia, CASI. There'll be a presentation on this in this workshop as well. High Tide SDS or the Deltares shoreline monitor. And just to conclude, here's a list of resources that you can use. So open source toolboxes. We created an open source community on satellite-derived shorelines called Satellite Shorelines. And here's different data sets on CoastSat, but also other toolboxes like CASI, ShoreX, and Deltares. So yeah, thank you very much for your attention. And I'll be available for any questions or discussions on the breakout session #1. Thank you.